Uh, our next speaker is Víctor, who's going to give a shorter talk about SIMD. SIMD is one of the things that you are going to get in the next version of the standard, which means that hopefully you will no longer need to use intrinsics for vectorization. Of course, if you think that auto-vectorization in the compiler is going to solve your problems, good luck. I don't see this is going to happen, but at least now we have a library interface for SIMD instructions, which in some cases will improve a lot your performance. If you survive to using SIMD, of course. So Víctor works for Scalian, and I found out recently that by coincidence we were born in the same city. Just a coincidence. Two C++ programmers in the same place. Okay. Okay, Víctor, thank you very much for coming.
It's Víctor from Scalian. I'm happy to be here for the first time. It's going to be my very first talk in my life in front of such a big audience, so bear with me, please. I want to thank Scalian for sponsoring this event one more year. I work as a consultant, C++ developer for embedded systems. In this company, we're dedicated to a lot of projects about artificial intelligence and big data, data science. So don't hesitate to take a look at our booth. Later I will expand a little more about us. Well, I'll talk first about myself while I show here the index of contents. I want to let you know, first of all, I'm not actually a computer scientist, nor a computer architecture specialist. In fact, I'm a physicist. Thanks to this background, I was motivated to do this. Well, this takes me back a little bit to my years in the university, where my first contact with programming languages was with Fortran 17. That language, believe it or not, was pretty good for number crunching. And we used to perform a lot of simulations and all sorts of modeling and reproduce physical phenomena with a computer, because you cannot always find an analytical solution to all the complex mathematical equations that run the world, Then, after that period in the university, by the end of my university career, I started taking a liking for C++. Then it was when I landed a job as a consultant. And until now, I've been specializing in this language. 2 years ago, it was my first time attending this event using STD CPP 2023, where I attended a workshop organized by Matthias Kretz, who is a member of the ISO C++ committee, international committee, and has been pushing driving towards the standardization of the SIMD utilities, which will enable us to get the most out of our hardware. And let's see a little bit about what this is all about. Actually, I want to let you know in case you have very high expectations, this is going to be extremely simplistic. I want everybody to live here. If you didn't know about this, you will know everything, I mean everything in a very simplistic way, and have no doubts about what I'm going to tell. First of all, these are the initials for single instruction multiple data. You know how a CPU works. It has different layers of memory, different capabilities, sizes, speeds. In order to perform a computation, the CPU needs to grab data from the memory and shove it into a register. And then, when you have to register, you can apply an operation on them to get an output, and you return that data back to memory. But, since a few years ago, we were receiving in the market of CPUs improvements which allow not this model of a single data, single operation. Instead, we can apply simultaneously the same operation over and over again to an array of data. That's the primary idea about this, all right? This can be very handy for certain physics simulations, where you happen to simply apply the same mathematical operations over and over again over a lot of data, because you have to divide your domain problem into pieces and then operate with those pieces, which computers are very capable of doing. We always lose some precision, but it's always dividing the domain to perform a discretization of the problem. It's a small figure to illustrate what I just said. In the processing unit, which is the register, taking data from a data pool, always contiguous in memory, and then apply the same instruction to a pool. Scalar processing is when we have a classical loop iterating over a typical array, grabbing data from memory, applying some transformation to it, adding some quantity, multiplying, whatever. But the SIMD processing, as I said, takes data and simultaneously operates over them. Let's see, what do you have it for? In order to leverage this, so many underscores, so ugly, right? Well, this is pretty much what we have until now. A little difficult to look at. Somewhere I will use a GMP library. It's a library in C for operating with big numbers. It has kind of a similar interface design where you have to create this. Cannot use the pointer. You have to create this kind of objects, special objects, to operate with the chunks of registers together in a pack. In this case, it's for 256 bits. These are instructions to load and align in memory data from memory into this special register to be able to operate simultaneously over them. And we create those things, vec A, vec B, which are called vectors. Please do not confuse, do not mistake it with the STD vector. It's called a vector, and in a certain way it behaves like it, but it is not what we know as a STD vector. So it's a little bit ugly. Keep in mind, we are prone to commit mistakes by jumping, as we do here in this loop example. We go in chunks of 8 by 8 because since we can load, we're assuming that the size of a float we want to operate is 4 bytes. So eight floating point numbers can fit into this register, so we jump over it all at once. So can we do better than that? Well, here is what we're going to get, hopefully, next year, if the ISO International Committee approves this. Keep in mind that all this is still in draft, so it's prone to change. But our main tool to deal with this is the class SIMD. Okay? It takes basically a parameter, a template, taking a type parameter, similar as in the standard library of containers. And then there's another second parameter, which is the ABI. I don't want to dwell too much in low-level details, but it controls a lot of stuff related to memory alignment, but mostly the size it takes in memory. But in order to operate in a very non-overhead way, for us, which are not specialists in computer science, we have a couple of convenience aliases, which are those I present this. It's a fixed size SIMD. It's basically an alias for the SIMD, where you specify the type you want. That's always you have to specify, and you just tell it how many elements do you need to operate at once. Then there is the native SIMD, which theoretically is the most efficient type to operate on the architecture you're targeting, to run your program. So this will be the vast majority of time what you are going to use. There's also the scalar alias, which simply boils down to your typical arithmetic type, your typical int. It's intended for when you don't know if you have to use SIMD or not, and you want to use write code portable. It's capable of working with your normal arithmetic types or in SIMD fashion, right? Let's take a little overview of what we're going to offer. So, take into account that when something is still in draft, you will find it on the most compilers out there in the market. You will find it under the experimental namespace, nested namespace within STD. STD, colon, experimental. And also the headers are placed in a subfolder called experimental /SIMD. So I've created in these small snippets an alias. It's also typical practice if you want to experiment a lot with them. It's called experimental for a reason. Alias namespace stdx equal std experimental. Okay, here we're going to assume creating a native SIMD, and I'm constructing it, assigning just a number. We're assuming that in this native SIMD, for the particular architecture I'm targeting here, let's assume it can fit 4 numbers, whichever is the size of the int. But the optimal, according to the compiler, is 4 integers which we can operate at the same time. Its first code is the broadcast constructor, which applies the same number to all the possible positions you can hold. Then second is object B. It's a constructor accepting a generator. So it's a callable, in this case lambda, whose signature receives an integer. This integer represents an index telling which of the items inside the SIMD are you initializing. So that's why you get 3, 4, 5, 6, because you start with index 0, 0 plus 3, 3, and so on. It will be called to initialize all the items within the SIMD register. And you can see compared to what we had before here, I think there is no point in comparison, right? So it's a very good syntactic sugar to allow us to express the equations we want to perform out as you will do with just a plain integer. So when you sum a plus b, you do a element-wise operation from 1 to 1. It's very similar also to STD val array, which we have always been having since C++03, although I guess nobody knows about it, right? Does anybody know STD val array? Used STD val array. Oh, that's another different thing. Okay. Hey, you have used STD val array? Great, good for you. You have nothing to learn from me. Well, more operations can have said, the typical, anything which can integers do, you can apply them to SIMD register. But also, as I say here, all the mathematical operations too are supported. All which are in C math. So you have trigonometric functions, exponential, lowering, and all of them will be applied whenever possible in parallel when you try to use this class, right? Next one. Probably for those new to this, the most tricky part to understand, but it's actually very easy. And one of you have used MATLAB to perform computations? Yeah, quite a few. Nice. Logical matrices in MATLAB in particular? Oh, well. And I'll go a little bit slower if you don't know what a logical matrices is. Basically, this class I'm presenting here, the SIMD mask, this is actually an alias for or a more convoluted signature, but in case you're assuming this object B I'm using here is a STD native SIMD, the optimal size for operating in your target hardware. This native SIMD mask is what you obtain when you try to apply a logical comparison to a SIMD object. In this case, you take a look at the right side of this assignment. B greater than 5. It means I am requesting to know which of the items in the B object meet the condition I'm expressing. Tell me which items are greater than 5. And it will return another object with the same size, or size in the sense of number of items it holds, filled with booleans, in which it will be true whatever item, at which position the condition I've been requested is true. So that's why it's false, true. Just because only the 6 and the 7 are in the position where they are numbers which are greater than 5, and the others do not. Okay, then if you got this pretty easy, you can use this mask to perform your typical if-else branching, to take decisions. You can get past this, you are almost ready to leverage all the power and usefulness which have all the SIMD can bring to your computation. Look, I have there an expression which is a where. Almost looks like a query in a database, but not. It will return, it doesn't return actually, but instead receives the object we want to operate as the second parameter, and it's taken by reference. It's going to manipulate the parameter we pass in the second place. I take the mask and say, hey, take B, take all the positions that indicated in the mask as true and apply to those in the position marked as true the operation that I'm indicating in the right side. So basically, I'm telling, hey, Mr. B, whenever you have someone in some position which is greater than 5, duplicate it. You can put any operation right here, any increment, summation, whatever, in order to manipulate your SIMD register, vector register, as you need, according to what you express in the mask. Sometimes this may become a little bit unreadable because we might tend to shove the b greater than 5 as the first parameter and then see another thing there. What's that doing? Well, maybe this way is a little bit more readable, but I hope you got the point. So that's why, as I said, only the 2 last elements, which containing the true values, are duplicated here, while the other 2 remain unchanged. Pretty easy, no? Nothing to be compared with the compiler intrinsics, because I have not said it, but the power of the standard library is portability across platforms and ease of use. So you don't need to get all the overhead of getting the sizes right and so on, thanks to the convenience aliases I have presented right there. And let us code in a more secure way. So let's see if we can apply to a particular problem. Well, first of all, we are going to see, I don't want to delve in too much detail because I'm not an assembly specialist. I barely can understand it, but here I'm comparing what you would get when the compiler does not apply vectorization. And in the right side you have, it might be wrong, okay? Because as I said, I'm not an assembly specialist. But those are the typical instructions in Intel syntax applied normally on your typical arithmetic types, okay? Then below you have the instructions generated by the compiler for an Intel processor. See all those move, DQ, it's also movement to load data from memory, but it's done in batches of 4. So that's why you see the Q, quad. So you see this Q, you like to tinker in Godbolt. It's a signal that your compiler has applied optimization, be it because you have explicitly used the SIMD instruction, or maybe the compilers have figured it out, because with -02, if you use GCC, I've been just practicing with the GCC. With -02, the compiler starts trying to figure out if there are ideal conditions to try to vectorize all your instructions. For that, it's extremely important to not have interdependency between the chunks of data you're operating. It needs to know how many iterations you're going to perform, and so on. So typically, if it's a multiple of the word size of the processor, if I'm not mistaken, it will try to apply it. But there is a lot of heuristics involved, very, very complex, and don't have the time or the top-notch knowledge to delve into it. Other instructions that you can try to look for are these move ups, add PS, mul PS. You see this PS is also a sign that it's applying SIMD instruction. There are different families which have been coming out, releasing into the market to add, greater capabilities for parallel processing into our CPUs. We will see later that this will benefit you even if you have just one core available. So, because all the experiments I've been doing have been with a virtual machine with just one core. So, even if you are working in an embedded environment, you can still leverage the power of SIMD. Your CPU architecture supports it. So, something to take into account in order to improve a bit the performance of your applications. Here is the exercise I came up with since I attended the Professor Matthias Kretz's workshop 2 years ago. Say, well, let's try our bets here. What is this Monte Carlo methods? Let's try to compute the pi number, which everybody knows about, right? Anybody has ever heard about the Monte Carlo methods? Quite a bunch. Okay, let me explain for all the rest of you who never heard about this. It's related to the casino in Monaco, indeed. It consists in solving problems which have a non-deterministic, deterministic outcome if you have enough evidence, enough samples, because in order to put it some other way, there is some non-deterministic cause modeling the event, so a single outcome is impossible to predict, okay? So you need to generate a lot and a lot and a lot of numbers. So let's see, sorry for the scrambled image. The exercise is very simple. To compute pi, we're going to generate random positions, a lot of random positions, because, as I say, we need statistical significance. You need a big sample. And you generate random numbers, pseudo-random numbers, in a procedural way. And they are uniformly distributed. Eventually, with enough generation of numbers, you will cover the area of a square in which a circle is inscribed. So the development, which everybody knows from elementary school geometry, we're just computing the relation between the area of the square, which is r, the radius of the sphere, divided by 1/4 of the sphere, because we're just in 1/4. So we're going to cover the whole areas. The area will approach to the number of total dots, and the area of the quarter of the circle will tend to be the number of dots inside the circle. So we just have to follow this algorithm, which is generating two pseudo-random positions between 0 and the radius, which is our maximum bound. And then we need to check that condition, which is the area of the circle, the Pythagorean relation. So if we meet that condition, you just have to increase the counter and repeat a lot of times. So let's see if I can take a look here. You want to check a little bit the code generated by the compiler in .bolt. You can see some places the instructions I mentioned it earlier. Well, outlining. And I've not done this the best possible way, because I've used a macro to switch if I want to use a scalar or not. I have to use the mask I mentioned earlier. But here, I'm just declaring an alias for a numeric type, and this will be a native SIMD. I just need to establish a max random number to be generated with care of not incurring into overflow when I want to check the condition. Technically, I just need to get an initial seed, but it should be our numeric type, which is a SIMD, because if we do not make it into a SIMD, we may not parallelize the generation of random numbers we have to generate, okay? So if it's just a scalar, we just call a random device to give us the first number of a sequence. The generator I've chosen is the linear congruency generator. It's an algorithm extremely simplistic, where we have this relation, recurrence relation. The next number in a sequence given by the previous number, multiplied just by a factor, summed by an offset, in this case 0, and apply a modulus. And just return, we return the modulus of this maximum random number we have set as an upper bound. We're working with 64-bit integers, and the max random number will be 16 bits, because when we check the Pythagorean relation, we might overflow. So we need at least 2 sizes lower than the bigger we can operate with. Okay. So this is the main algorithm. Just initialization, setting a number of iterations. I will compute the maximum iteration from the total experiment we want, which is a constant I had at the top of the header. Yes, it's not wonderful so for this time. This is how physicists do it, okay? Just numbers and numbers and numbers. And then I compute the number items per SIMD instruction, items per vector, which you can query with std size. Apply std size to a SIMD object and will tell you how many items are there. So you divide the total experiments you want by the items per vector. I ensure that they are divisible by 0 with a static assert, okay? Oh, divisible by 0, no, I mean, they are perfectly divisible, okay? Because otherwise, if you compare it against the scalar solution, it will be doing less iterations than it should do, computing less number than it should do. So we're effectively reducing the iteration of the loop because we are operating more numbers at the same time. We do it in scalar, we do it one by one, unless the compiler optimizes. So we just get the 2 numbers, as I say, 2 coordinates, and then I apply here. You can see the contrast between the typical branching if-else. If it's inside the circle, because x squared plus x squared, blah, 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 increase a counter. Here you see the word expression. If we meet the Pythagorean relationship, then take the count, SIMD instruction, and then add 1 to it. In this case, I've been using x64. So using native SIMD, you can fit up to 4 numbers in here, okay? So you just repeat, and then take the final results to compute pi. By the way, here is the result here when you have all this iteration, 3.14, 17, good enough, we could say, all right. Let's see this. This is the results I plot with different configurations of the compiler, and here I saw something extremely important. In this, there are 3 almost overlapping without significant difference, where I use scalar, I use SIMD without tuning the architecture of the compiler. So when I invoke GCC 14, those are the specifications you can check. I did not set the -march flag, so it did not optimize properly until I fall into this and say, let's try to set -march native. Or you can also put -march alderley, so it can fine-tune for your CPU. You don't leave it set, it will apply generation of generic instruction for any x64 processor. So you're leaving out a lot of instructions to leverage the power of the CPU. And then suddenly the SIMD native object I presented, when you don't tune the architecture, it can hold just 2 integers to operate. When you tune for the native architecture, you suddenly have up to 4 numbers to operate at the same time. So this explains partially the improvement in the significant improvement in the decrease of time. Obviously, the complexity is linear. The more iterations you do, the more time it will take. Probably will be some bottleneck out there. Could not figure out what it is. Here is another experiment I did using native SIMD size, okay? But the execution time.
Running out of time.
Here, I took the class where I mentioned previously with the size, fixed size, and say, hey, let's compile for different size and run for a fixed number of experiments and see what it does. Let's see if beyond 4, which is what the native architecture suggested, I get some improvement. And yes, it looks like there is an asymptotic value for which you cannot improve anymore. In fact, you try to request a SIMD to fit 64 elements, the compiler will halt you and say, oh no, you cannot operate with 64 elements. 32 is too much already. So take that into account if you play a lot with the fixed size. This is the more convenient type in case you need portability between different architectures and so on, but it might not be the most efficient. But in this case, curiously, it has 1. You increase a little bit beyond 4, you get the most out of it. Let's sum up a little bit. All this, best practice, always benchmark. Never assume you're going to always get good results just for applying SIMD. You need to know that your data are actually independent from each other. Otherwise, you cannot apply parallel operations on each of them. As I said, use fixed size for portability. And for native-only programs, try to contrast the native, what you get with native SIMD with fixed size, okay? I say, try to avoid always branching to match if-else conditioning because it must be straightforward operation application over a large set of data. Always keep in mind that if you have very far away locations in memory, you might incur in that old enemy we have called cache miss, okay? Because if you try to operate fast, maybe you cannot because the CPU is waiting for data from the memory to arrive from the L2 cache or RAM. So that's an important bottleneck that you cannot solve with the SIMD. Well, let's sum up by mentioning Matthias Kretz, who has been pushing for this and showing about this. Here's a link. I will provide this presentation in case you want to take a look at it, but it has much more applications just rather than any other numerical simulations, but image processing is just one of them. And anything that you can do over and over and over again, very possibly SIMD can be taken advantage of, all right? Oops. There you have the GitHub for Professor Kretz, where he also has additional libraries beyond what will be included in the standard to help you operate with these utilities. That's all. Thank you very much for attending.
We are a bit behind the schedule. I will have time for one question.
Hi. In the case we have different build, for example, 2 different build targets with different architectures, with different specific accelerators, how can then define the size and how can we tailor the solution for both? Is there any option? As you said, I think you said you use some flags over there, but is the only...
I could not have enough time to analyze what the binary, the assembly have been yielded, but maybe I did not perform all the simulations correctly. Maybe because having one core interferes with the operating system, and maybe I should have done more repeated experiments in order to leave out any possibility of random interference in order to perform a better benchmark. Keep in mind, it's possibly my very first benchmarking ever. But, always try to benchmark however you can with at least with ST Chrono, Google benchmark if possible, and that's it. You do not know until you try it.
Okay.
There's no.
So
Very difficult to predict. You know your data are independent, and you can apply the same operation on them. Try to use SIMD, but as Jan Krasinski said 2 years ago, always benchmark, never assume. Right?
Okay, so I will be like attacking two different problems, right? The first one will be the first architecture, and the second one will be the second one. So specific. Okay.
They are completely independent. So you can generate independently random sequences, and the domain of the problem is independent. You just want coordinates. I want them all at the same time, as much as possible.
Okay, thank you. Thank you very much.
Just say, we're hiring C++ developers, so please come to our booth and
everybody is hiring. Okay, thank you.